and he's going to be talking about some of the work he's been doing on multi-agent systems with applications to space. Before he came here, he got a PhD from the University of New Hampshire in 2020. And after that, he was at the University of Vermont and the University of Grenoble Alps in France, beautiful place where we met. Mm-hmm. And now he's here. So, Himadri, welcome, and the floor is yours.
Yeah. Thank you, Professor Ricardo, and thank you everyone who has managed to join us in person and also those attending via Zoom. Today, I'm very excited to be presenting at CPSRC seminar, and my talk today is on distributed control and optimization framework of multi-agent systems in space applications. Distributed control has been looked at from various scientific communities. It's inspired by the collective behavior exhibited by biological species, for example, flocking of birds, schooling of fish, and so on. In industrial automation, multiple autonomous agents are made to work together to collectively achieve a group task. In this case, the control strategy for each agent not only relies on its own information, but also the information coming from its neighbors. So this gives enhanced efficiency, flexibility, and reliability compared to a centralized control, compared to a large, complex, monolithic controller used in centralized scheme. So this avoids the possibility of single point of failure. The example of distributed control problems are numerous, but just to name a few, we note here the formation control of satellites in Earth imaging problems, ocean mapping by underwater vehicles, and in precision agriculture by a swarm robots. Each of these robots for precision agriculture could be tasked with different responsibilities. A group of agents could be tasked with seed planting and monitoring the irrigation system, and the other group could be looking after the plant health, vegetable harvesting, and mechanical pollination. So by coordinating these actions, agricultural tasks can be efficiently carried out by this group of cooperative robots. Distributed control problem can be formalized into multiple control theoretic areas. For example, distributed sensing, consensus synchronization, formation, cooperative tracking, or output regulation. Consider n number of agents with the agent dynamics xi dot equals fi xi ui, where xi is the state vector, ui is the control, yi is the output measurement, hi is the output function of state and the control ui. The control for each agent is designed based on the information based on agent's own information xi hat in the absence of actual state information xi, and also the information that comes from its neighbors xj hat in the absence of the actual information xj, where j is the neighbor of agent I. The term neighbor will be explained in a slide, in later slides. For formation control problem, the control signal ui not only depends on the neighbor's information xj hat, but also it takes into account the desired displacement vector between two agents I and j. For consensus problem, the goal is to asymptotically stabilize the set A, where set A is set of points where the state vector for all the agents converges to a common point x star. And for the formation control, the goal is to stabilize the set A, where set A is those set of points where the displacement between two agents matches the relative desired relative displacement between those two agents. A cooperative tracking problem is very similar to leader-follower tracking problem, where we have a leader dynamics w dot equals fw, And there is some leader signal that the agents need to track. The tracking error is defined as EI, which is also known as regulated output. The control objective here, UI, is the control objective is to asymptotically stabilize the set A such that the regulated error asymptotically converges to 0. The control law UI that we saw in the previous slide could be found by minimizing a local cost function Ji subject to system dynamics and other constraints. For consensus problem, it could be of this form, where Wij is weighting positive weighting factor, and T is the prediction horizon. For formation control case, it could be minimizing the displacement between two agents relative to the desired displacement Dij. The constraints are in the form of there could be many constraints, but it could be categorized into 3 areas: network constraints, physical constraints, and system-specific constraints. Network constraints could be the communication network could be time varying. It can incur some latency in data transmission. While transmitting data due to limited bandwidth of the network, there is a possibility of packet drop-off. Data could be exchanged between the agents in an irregular manner, so that gives rise the possibility of data intermittency. And also there are situations where cyber attacks can occur. Denial of service is just one of them. There could be physical constraints such as lack of detectability, where agents do not have access to the synchronization signal that they want to synchronize to. There could be parametric uncertainties in the agent dynamics. The agent's actuator and sensors could be saturated, or they may suffer from quantization issues. There are some system-specific constraints. For example, in formation control, collision avoidance is one of the main requirements that are usually considered. In terrain mapping by a group of mobile robots, surface and terrain constraints also are also accounted in. In spacecraft formation, we explicitly take into account the limited onboard processing and also the propulsion limits. In today's talk, we are going to consider explicitly switching communication network, lack of detectability, collision avoidance constraints in formation control problem, collision avoidance and propulsion limits in formation control problem. So based on this, our first talk is on distributed state estimation problem of a linear time invariant system under directed switching networks. So in the first case, we consider 2 constraints, switching communication network as well as lack of observability. In the second case, we are going to look at fuel optimal trajectory planning of satellite swarm in low Earth orbits, where we consider the constraints on actuation or the propulsion limits, also take into account the possibility of collision with other neighboring satellites or agents. The third talk is on autonomous control of spacecraft in rendezvous and proximity operations. So this is the basic presentation outline for today's talk. Consider a linear time invariant plant P of this form x dot equals ax, where x is the state vector. Agents, there are n agents, each of them measuring part of the plant state vector x through the output equation yi equals cix. The main challenge is ACI is not observable for any I. So there is a need to design an estimator function Fi that gives a reliable estimate of the actual state vector x. This estimator function Fi, as we can see here, not only relies on agent's own information xi hat, but also relies on the information that comes from its neighbors xj hat. However, the communication of network of agents is time varying in this case. The communication network transitions from one to the other by a piecewise constant switching signal sigma. And in between two consecutive switching instants, the configuration remains constant. The switching sequence is a sequence of switching times T0, T1, T2, T3, which satisfies a minimum dwell time bound tau bar. An example of switching communication topologies is shown here between the time T0 and T3, where the first switching signal sigma equals 1 is active between the time T0 to T1. From T1 to T2, we have sigma equals 2, and from T2 to T3, we have sigma equals 3. And the communication topology is different in all three cases. So in the previous slide, we said that the plant is not locally observable to any agent. However, the pair AC bar has to be observable. C bar is the combined output measurements by all the agents. It is also known as collective observability assumption. So even though none of the agents can locally independently estimate the plant state vector out of its own independent effort, but it can collectively estimate the reconstruct the plant state vector. OI is the observability matrix for ACI with its rank given as nu I. So this gives the dimension of the observable subspace calligraph SI. So if n is the dimension of the entire space, then n minus nu I is the dimension of the unobservable subspace. Since we mentioned that all the agents collectively reconstruct the plant state vector, so by assumption 1, intersection of calligraph UI is an empty set. Let UI and SI be a matrix whose column vectors form an orthonormal basis for calligraph UI and calligraph SI respectively. The reason I introduced the concept of observable and unobservable subspaces here is that we need to decompose the state vector of each agent, estimated state vector of each agent along observable subspaces and unobservable subspaces. And we have to analyze each of these components separately. Now on to assumption 2, the plant, the system is marginally stable. In consensus problem or in distributed control problems in general, we do not really want our agents to track an unstable mode of the plant or the leader. Also, we do not want the plant to be stable as well. Otherwise, it would be a trivial stabilization problem. It will not be a distributed control problem. So in between two extremes, we consider that the matrix A has all semi-simple eigenvalues on imaginary axis, or in other words, the system dynamics of the plant is marginally stable. We consider two scenarios when the plant measurements from the when agents measuring the plant happening continuously at all times. So based on that, a distributed estimation protocol is established where the estimated state vector is given xi hat. This resembles Leuenberger observer, but except for the fact that it now takes into account the information exchange with the neighbors. G. GI and MI are respectively observer gains and scaling matrices which are carefully designed, and mu is a positive scaling factor. Aij sigma represents the communication weighting factor between communication weight between I and J. We now consider scenario 2, where in the previous case we said agents measuring the plant continuously, but in scenario 2, agents measuring the plant only intermittently at discrete instance Ts. In this case, a distributed estimation is given of this form. I would like to I would like to point out here that the inter-agent communication is piecewise continuous as in the previous case, but this estimation experiences a jump when it receives new measurements from the plant. So that's why it's of hybrid nature and given by the jump term xi hat plus. And this occurs when it receives a new measurement from the plant. Directed communication diagram G sigma consists of the vertex set V and H set E sigma under the switching signal sigma. Communication link from J to I is given as communication link from J to I is active when corresponding communication weight Aij sigma is 1. It is 0 otherwise. The neighborhood set of an agent I is all those agents from which agent I receives some information. And directed path between two agents is a sequence of directed agents that exists between these two nodes. Starting from any particular switching instant TL, K union digraph is the union of all K digraphs that follows from the switching instant TL. So in this case, in between time T0 to T3, the union of three digraphs is a strongly connected graph. Let the plant be labeled as an additional node designated as node 0. Then the vertex set B bar is 0 union B, where B is the set of agents. And similarly, we can take into account the outgoing nodes from the plant to the agents and denote the entire edge set as E sigma bar now. And our overall communication diagram is G sigma bar. Laplacian matrix is denoted as L sigma bar. It has all 0 first rows, which comes from the fact that the plant doesn't receive any information from the agents. One property for Laplacian matrix is that it gives 0 row sum. So based on that, it has delta sigma 1n equals H sigma 1n, where 1n is a vector is an n-dimensional vector of all ones. Delta sigma is a diagonal matrix with communication weights for the communication weights between the plant and the agents. H sigma is a matrix which has all non-positive off diagonal terms. Negative version of such matrix is called a Mechler matrix. So minus H sigma is a Mechler matrix. This matrix is quite important, and for proving some of the stability results, we'll have to revisit this matrix multiple times. So consider a switching system given in equation 1, where we have this H sigma matrix. If the leader or the plant is reachable to all the nodes in frequent time intervals, then we can show that the origin of system 1 is globally exponentially stable. Based on that, it could also be extended to another form by some minor transformation from Z to Z bar, and show that the origin of the dynamics given by Z bar dot is also globally exponentially stable. This corollary will be required in proving our main results later on. And in our current case, to ensure that all the agents receive, just to ensure that all the agents manage the components that they are not estimating themselves, they can find it out from others. This is established by assumption 3, which says that all the nodes are reachable from one another in some frequent time intervals. Now for scenario 1, this is the structure of the estimation protocol that we had. And now we do some coordinate transformation, and we have this estimation error dynamics given by xi tilde dot. We purposefully design our observer gain and weighting matrices in a specific way, so that for the observable component, so the dynamics associated with the observable component, agents do not need to communicate with others. So the diffusive coupling term for that case is 0. However, for the unobservable component, it needs to receive information from others. So to enforce that, we start with a specific choice of GI and MI. In distributed state estimation problems for static networks, we actually design GI and MI that that ensure the stability of the entire system. But in this particular case, we start with a specific choice of GI and MI and then show that the system is stable. A sigma I matrix that is used in GI and MI satisfies similar to Kalman observability decomposition lemma. So the estimation error based on this observability decomposition, it is decomposed into observable parts as well as unobservable parts. Observable component is associated with SI transpose tilde XI, and the unobservable component is given by UI transpose XI tilde. Now, by the joint observability condition, we see that the unobservable subspace of one agent is the observable subspace of the rest of the agents in the network. So we substitute that information in here, and eventually we get from each agent dynamics, we get n unique projections along n observable subspaces. And here so here we have the observable. Here is the dynamics of all agents along the subspace calligraph SI. So this is the example that we have seen before. Now, when we do observability decomposition and we decompose the state vector, estimated state vector into observable and unobservable components, this is how it looks like. The observable components are marked in colors. We see from here that the component that agent 1 observes is not observed by any by any of the other agents in the network. And similarly, the component that agent 3 or 2 observe, that is unobserved by the other agents in the network. Let calligraph S1 be the observable subspace of agent 1, and which is marked in red. Calligraph S2 is the observable subspace or the observable component of agent 2, marked in blue, and S3 is the observable component of agent 3, marked in green. So by this observability decomposition, and when we gather all the components from the agents along each unique observable subspaces, then we end up then we can reduce the entire distributed state estimation problem into n decoupled estimation problems. So here, since we have 3 agents, we can reduce the problem to 3 decoupled estimation problems. And in each of these decoupled problems, there is a master node which observes this component, and this component has to reach to the other agents in the network. So this is these are the projections along the subspace calligraph SI for all the agents. It could be written in a more compact manner. The first part, SI transpose tilde XI dot. In this dynamics, we see that the matrix AI bar minus GI bar CI bar is Hurwitz by a suitable selection of GI bar. Then we can show that tilde XI converges to 0. And then by using input to state stability like argument, if we can show that the if we can show that tilde x minus I, this dynamics is globally exponentially stable, then we can prove the stability of the entire system. And one thing that in tilde x minus I in this dynamics, the system matrix is of the same form that we saw in this corollary. So by ensuring that all the agents or all the nodes receive information from the master nodes in their decoupled estimation level, then the origin of the system could be shown globally exponentially stable. For scenario 2, we start with the same decentralized design of GI and MI, and that allows us to decompose the state vector into observable and unobservable part. Here, the unobservable part is same as before. It's piecewise continuous dynamics as before, but the observable component is of hybrid nature. So it can be written in a more compact form as before. And the observable component, it experiences jump when there is a new measurement from the plant. So it could be put together in a hybrid system notation where the flow map is given by Fi and the jump map Gi. Here zeta I comprises of this observable state vector tilde xis, and also there is a timer variable tau that dictates when the jump will occur. So here we have the flow map, jump map, flow set, and jump set, and this is our equilibrium set AI. So when tilde xis goes to 0, the system is globally exponentially stable. If you remember in the previous case, we said we designed GI bar by showing that the matrix AI minus GI bar CI bar Hurwitz. But in the current case, we design GI bar differently since we have the hybrid dynamics. So we using Lyapunov based stability analysis, we end up getting some LMIs by using some algebraic manipulations and using convex polytopic embedding approach. So that gives us all the design parameters for scenario 2. The scheme can be illustrated better with a numerical example. We have a 3 inertia system, 1, 2, and 3, where Ks is the spring constant and J is the moment of inertia. C1, C2, C3 are the output measurements that each agent receives. And the switching communication diagrams is given on the right, where sigma varies from 1 to 3. In this particular example, we assume that these 3 diagrams are repeating periodically, but this is not required this is just for this illustration purposes. We don't really, to prove our result, we don't really need the periodicity of diagrams. Here, the transmission time interval satisfies the minimum dwell time bound tau bar, which is 0.2 seconds. And there is a maximum time T2, which is 0.5 seconds. So we verify all the assumptions are satisfied, and then we design our observer gain and weighting matrices for both the scenarios. And this is the result that we get. This is the normed estimation error vector for scenario 1. And we can see that this is globally exponentially stable, and it is bounded by some exponential bound here, and the decay rate is 0.33. For scenario 2, we see the estimated state components. I just give here the first 2 for each agent. And we can see here that there is a jump for scenario 2 whenever there is a new measurement coming in. So in this presentation, we saw distributed state estimation problem of a jointly observable linear plant under directed switching networks. We considered both cases continuous and sporadically available plant measurements. We decompose the state vector into observable and unobservable component. By using joint observability condition, we decompose the state vector of all the agents along n unique observable subspaces. In this work, we considered that the inter-agent communication is piecewise continuous, but in future, we would like to extend this to purely intermittently discrete inter-agent communication as well.
Would you questions now or should we wait until then?
I can take the 5 questions.
Yeah, go ahead.
I was just curious, whether the work that you show by Will Rain or
Mhm.
they provide any explicit equation for the computation of the minimum dwelling time, or if you did something like that, because I'll imagine that there is a
Mhm.
direct relationship between that and, for example, your initial estimation error.
Mhm. So
but-
you mean
what we call sometimes
You
you
mean
call it
distance
B,
of?
sometimes you call it yeah, you call it, I think you call it eta, or like
No, here there is no dual timing here. So V is like the time interval within which I say like the leader is connected to all the agents. Or so let me put it in a better way. So the leader's information reaches to all the agents in that V time interval. But I'm not saying this is the dwell time.
you're right, you're right. More like in your example, you showed you had a time T2, and you
Mhm.
had also a time, a minimum amount of time that had to happen for each of the communication configurations, right?
This one?
You call it tau, right?
Tau bar. Yeah.
Okay, tau.
Mhm.
Do you compute? Do you have any explicit formula to compute the dwelling time?
No, that was not really part of this work. We just assume like there is a minimum dwell time that exists. There is no we just need to ensure that there exists some sort of minimum dwell time. That's we do not use that information in the design of our observers. So
Because I'll imagine that there has to be a specific amount that each configuration has to stay on,
Mhm.
so you can have
the
enough-
information is so exchange is meaningful. Like
Right.
it's not happening at discrete instance.
Exactly right.
Yeah.
Yeah.
So that's the assumption. Like it is piecewise continuous. Intelligent communication is piecewise continuous, but we are changing here the plant agent communication. Plant agent communication could be continuous as well as could occur at isolated time instants.
Okay. And one more question on this example. So it seems like each of these agencies contributing to a part of the general state estimator, right? Like
Yes.
it's like if each of them had an estimation of the other two states that they don't know,
Mhm.
and
Yeah.
then they form the global estimation of
Right,
the system,
right.
right?
Yeah.
So the way that I see that is like as a centralized kind of
No,
version of estimation.
so we say centralized or decentralized based on how we design our controller or the observer parameters here. So if you look at our control design, so here, let's see. Oh, sorry, the observer design. So this is purely decentralized. It doesn't use the information.
For the control design.
Yeah. But using this observer gains and the scaling factor MI, agents, the observable component of the agents
Mhm.
are they do not receive any information from other agents. That is how it is made. But the unobservable components receive information from the other agents. So because if an agent is observing some component of the plant itself, why doesn't it need to receive any further information on that particular state from others? So that motivates the particular design choice of GINM. But the unobservable component, since it doesn't like for that case, you need to receive information
So at the end, you can prove stability without showing that the estimation error converges to zero, right? You don't need that necessarily.
No, we have to.
Okay. Yeah.
So with this specific design choice, we start and then we show like how the scheme works, how the unobservable component of one agent is compensated by the observable components of the other agent. So that is how we show using some assumptions on graph theoretic assumptions we had, like assumption 3 is there in this. So by that, show that this scheme works and estimation error asymptotically converges.
No, that's good. Thank you.
So in the second part of my presentation, I talk about computationally efficient trajectory planning problem of satellite swarm in low Earth orbits. Given an initial and final formation pair A and B for a satellite swarm, the objective is to develop a trajectory optimization framework that allows the agents to determine the fuel optimal final configuration and thruster commands that allow the satellites to move from formation A to B while avoiding inter-satellite collisions along the way. So the first part of this task is to figure out the fuel optimal final configuration, like in final formation B, which positions each of these satellites will occupy. So this is called as swarm assignment problem or path assignment problem with acronym PA. And then the satellites move from their initial position to the final position while avoiding collisions along the way with other neighboring satellites. And we have predictive control framework to mitigate any modeling errors. We consider a couple of computational requirements. For example, computational efficiency is one of them. Is our optimization framework scalable to a swarm size upwards of 100 to 500 and so on? And can we guarantee robustification against modeling uncertainties? Before I move on, I would like to mention that we need to clearly distinguish this formation reconfiguration problem than traditional formation control problem. In formation reconfiguration problem, group of agents need to undergo a sequence of formation patterns. So not only they rely on the relative information between the agents, but they also need to be given at which point this formation 1 will occur, which point formation 2 will occur, and so on. In regular formation control, the communication between the agents is rigid. If I and J are communicating now, that communication configuration, so that configuration remains rigid till the end, until the point they arrive at xi minus xj equals their desired displacement. But in formation reconfiguration problem, they are also given the final set of points for each formation pattern. In this particular case, we also do not clearly know where, but we also do not clearly know which final positions each satellite agent will occupy. So that's also that is also explicitly considered in our optimization or planning framework. There are 3 computational challenges to this path planning algorithm. In general, the relative dynamical model of satellites under orbital perturbations is nonlinear. But to simplify computations, we need to use some linear state space constraints for which we review linear relative dynamical motion of satellites, and we evaluate the model accuracy relative to high fidelity nonlinear model. But I will skip this part as we don't have much time to discuss the rest. The second part is the exponential time complexity of coupled assignment with trajectory optimization problem. When the assignment problem is included within the optimization framework, it exhibits exponential time complexity, as we can see on the right. Only for 7 satellites in a standard Windows computer, the average computation time is about 2 minutes. So when we use FPGA or other microcontrollers, it's not surprising that the computation time will be even more. So there is a need that we need to decouple this assignment problem from the trajectory optimization framework. Furthermore, collision avoidance constraint, formulating collision avoidance constraint is a non-convex problem. So there are 2 approaches. Either we convexify this collision avoidance constraint, or we change our final configuration in such a way that as the agents go from formation A to B, they avoid collisions along the way. So this is the overall framework. This is the trajectory optimization framework, where we have assignment problem and also collision avoidance included in it. So we are minimizing the cost. So we are minimizing the fuel consumption by all the 3 thrusters for all the agents during the prediction horizon N. It satisfies the state space constraints. This is a linear dynamics, and this is what we have identified, and I have skipped for today's discussion. And then we have this path assignment constraints. This part determines which of these final locations will be occupied by the satellites. Here Bij is a binary variable. And now we have actuation constraints and slew rate constraints on the propulsion. Collision avoidance constraints is a non-convex problem, and it's given here, where RSAFE is the safety radius that each agents need to maintain from the other. So we have, depending on how we deal with the collision avoidance task, we have proposed 2 approaches. The first one is find collision-free trajectories to fuel optimal final assignment. So first we find fuel optimal final assignment, and then plan for trajectories to go to this fuel optimal final assignment by avoiding collisions. So this is trajectory planning 1. In the second case, we change our final configuration in a way that satellites, as they plan to go from formation A to B, there are no threats of collisions along the way. We compare the fuel optimality, communication, and computation time complexity of both approaches. For TP1, we first find the minimum fuel final configuration, and then solve this trajectory optimization problem considering collision avoidance to find feasible collision-free trajectories. In the second case, we consider collision-safe final assignment, going towards which there is no collision risk. And then we solve just trajectory optimization problem to get there. In both cases, this step is common, step 1. In this step, each agent computes the fuel it might need to occupy each of these positions in the final formation. So for example, satellite 1 computes it will need F1A amount of fuel to get to position A, F1B to get to position B, and F1C to get to position C. Similarly, agent 2 computes computes the fuel cost that it required to occupy the positions in the final formation, and similarly for agent 3. For this step, each satellite solves n decentralized linear programming problems in parallel. And this gives us the fuel cost matrix F. This is an n by n matrix. So once we have this, then we can solve a minimum fuel assignment problem, like which configuration is ideal or fuel optimal for the entire swarm. And this is a centralized computation. And this gives us the final positions that each satellite will occupy in formation B. Once we have that, then solve a minimum fuel trajectory optimization problem subject to the state space constraints, actuation constraints, and collision avoidance constraint. This is distributed computation. And once we solve this, we get optimal control UC star that we apply on actual satellite model. And we keep repeating this step until we nullify the presence of modeling errors or unmodeled disturbances. One thing I would like to mention here is that the collision avoidance constraint, as I mentioned before, is a non-convex problem. And we have used an affine approximation of this collision avoidance constraint in this form. And we solve this distributed trajectory optimization problem we saw in the previous slide by sequential convex programming. So for the first step, where each agent computes this fuel cost matrix, not each agent, the fuel cost matrix F is computed in a decentralized manner, and it scales linearly. The second stage is a centralized problem where all the agents together find where all the agents together find out what is the fuel optimal final configuration. This is a centralized computation, but if we look at the computation time, it's very, very small, even for the satellites, even for the swarm size in the upwards of 500. And then we have this distributed trajectory optimization problem where each agent shares their position information or state vector with other agents and solve this distributed TOCA problem, considering the convexified collision avoidance constraints in it. And this also scales linearly. So in this case, we see that step 1 and 3 scale linearly. Step 2 has a very small computation time. Also, one more thing that we have found out in these experiments, that coupled PATO problem has an exponential time complexity, as I presented before. But when we decouple into two parts, path assignment part separate from trajectory optimization framework, we compute the solution, and we find that the minimum fuel solution for the decoupled case is same as the coupled problem. Let us consider a numerical example. There are 9 satellites starting from an initial projected circular orbit, PCO. 4 of them end up being on final PCO1, and the rest 5 move to final PCO2. When we do not explicitly consider the collision avoidance constraint, we see that the inter-satellite distance is violated between the satellite pair 15, 19, 28, 37, and 69 in the second figure, and the minimum safety distance was set to 75 meters in this case. So these satellite pairs violate this safety distance. But when we implement our trajectory optimization problem with collision avoidance, considering collision avoidance in it, then the inter-satellite distance obeys the specified distance of 75 meters. And on the left, we show the convergence of sequential convex programming. And this is the trajectory planning framework 2. In this case, we consider the possibility of collision avoidance in the assignment problem itself, and find out the collision safe final formation configuration. And then once we solve that, we know what the terminal locations are. Then we solve the trajectory optimization problem. And similar to the previous case, we implement a shrinking horizon model predictive control to nullify the effects of any modeling errors or disturbances that are present. And here we have a numerical result for TP2. And in this case, we see that this is the inter-satellite distance, which adheres to the safety requirement. In case if, this optimization problem in both cases, TP1 and TP2 can be infeasible in some cases. To guarantee that it is feasible all the time, we can penalize the violation from the safety requirement and include that in the objective function. And here we compare the fuel cost between two approaches, and there is no significant fuel cost error between TP1 and TP2. And we also compare the computation time and communication complexity of both approaches for the swarm size up to 100. And we find that with increasing swarm size, TP1 and TP2 give comparable results on computation time for the swarm size up to 55. But after that, TP2 grows much faster compared to TP1. And it's obvious because for TP2, we solve a mixed integer linear programming problem. And when we include binary variables, they are not as computationally efficient as the linear programming or other convex problems. So based on computation time complexity, TP1 is better than TP2. But when we take into account the communication complexity, since TP1 is a distributed approach, it requires more communication than TP2, and it shows clearly on the second figure. But if we stick to swarm size between 50 to 60, then based on these two figures, TP2 is better if we compare both of them, because the communication required for TP2 is really small and the computation time is not that large. And this is the result of SHMPC controller that mitigates the effects of any modeling error or disturbances that are present. If we do not take that into account, then we see that there are some terminal errors. We predict that we have reached to the final point, but actually, in reality, we have there are some terminal errors between 2.29 meter to 3.41 meter for satellites 1 to 3. But when we incorporate this, then there are no terminal position error, or the error that remains is negligible, less than 1 centimeter. So in this part of the presentation, we saw fuel optimal trajectory planning algorithms to find collision-free feasible paths. TP2 is preferred for a medium-sized formation, while TP1 can be used for a large formation size. And we have seen SHMPC reducing the presence of unmodeled disturbances and modeling errors. In this, in previous part of the presentation, we considered point mass model of the satellite. But in ideal situation, we need to take into account the rigid body motion of the spacecraft. So this is what we cover in the third part of the talk. Here we are going to see autonomous control of a spacecraft in rendezvous and proximity operations. Here, a chaser spacecraft need to dock with a target that is on low Earth orbit. There are 3 different phases of operation. pre-capture phase, when the chaser spacecraft approaches from far off distances, and capture phase is when it docks with the target, and post-capture phase is when the chaser spacecraft performs some operation on the target spacecraft. So this is called post-capture operation. For rendezvous operation, the distance from the target spacecraft varies from 10 kilometer to 1 kilometer, and for docking operation, it starts from 1 kilometer distance, radial distance from the target. For rendezvous phase, we consider relative spacecraft translational motion only. Since it's approaching from far off distances, we don't really need to include any, we do not need to include the information on rotational motion. We need that information only when it is too close to the target. And then there are input and state constraints and obstacle avoidance constraint. It has to avoid obstacles of the space debris that are present. The expected behavior is that the controller that we design for rendezvous phase, that brings us to a neighborhood of a set point around the target. From that particular set point, another controller kicks in that is responsible for the docking phase. So in that docking phase, we consider both the translational as well as the rotational motion, because as I mentioned before, in this particular case, we are focused on the rigid body dynamics. Also, we consider the impact model, considering contact forces between target and chaser. We have some input and state constraints, line of sight constraints, that as the chaser approaches the target, it has to be within some line of sight cone, and it shows efficient transient performance locally. So our objective is to develop an optimal strategy that allows us to augment these two types of controllers tailored for different phases. So for example, HKD is an MPC controller that are responsible for the docking phase, and HKR, this is the controller for the rendezvous phase. HKR brings us closer to the set point, which is Z star. And from that point to Z star is taken care of by the docking controller HKD. Our objective is to determine control log UC such that optimal trajectory converges to this point, Z star. And on the right, we have a uniting hybrid MPC framework. Depending on where Z star is located, a switch is triggered. So not only we have to design our controller, we also have to design the switch as well. Here, our overall controller KC is of this form, QHR plus 1 minus QHD. When Q is 1, when Q is set to 1, then the rendezvous controller is active. When it is set to 0, docking controller is active. So starting from any arbitrary point, I have marked with cross. Epsilon R is the set where the rendezvous controller can converge globally in a finite flow time. There is a set where gamma D, where it switches from the rendezvous controller to the docking controller, and this is shown here. The blue trajectory is the trajectory under the influence of the rendezvous controller, and it gets switched to the docking controller once it hits the set gamma RD. And gamma D is the basin of attraction. So basically, we need to make sure that epsilon R is contained within gamma D. And these are the state space constraints for rendezvous problem. And similarly, for the docking problem, we have state space input constraints, states constraints, and we have rigid body dynamical motion and the contact collision model between these two bodies. I would like to mention here that using point mass model, we have all the ingredients for the rendezvous phase we saw in the second part of the talk. In the docking phase, we have we have the state dynamics, the rigid body dynamical model, which is clearly laid out. And we are currently working on this jump part when two body collides, the motion with which both the spacecraft bounces off each other. Here is an example, chief and deputy, where PC is the docking port of the chief. The PC vector points to the docking port of the chief, and PD is the docking port of the deputy. When they dock, we want PC and PD to coincide, or rho to go to 0. Also, we want the angular velocity between deputy frame and chief frame should be 0. And also the relative orientation between the deputy and the chief frame should go to 0 as well. So this is what is shown in the numerical results. And in our current work, we are working on to develop the collision dynamics of two spacecraft. And we also have to design a switch mechanism to transition between different controllers. So that's that. So to summarize our talk, we have seen distributed control and optimization framework of multi-agent systems under various constraints. We saw formation reconfiguration control problem under switching networks. Compared to the second case, where we focused only on the point mass model. For the third part of my talk, I presented rigid body dynamical. We considered rigid body dynamical motion of spacecraft in solving autonomous rendezvous and docking problem of spacecraft in RTO. In future, we would like to take explicitly into account the limited onboard processing capability in our control and optimization framework. So that's that.
Thank you for the talk. Question for Himadri? Somebody in the chat maybe, but
I have a question. For the past planning work, when you're saying you decouple planning problem into two steps, right?
We decoupled the problem, like assignment problem was coupled with the trajectory optimization problem. So we decoupled that.
Yeah. Have you ever considered that the decouplation will decrease the size of the solutions? Because I don't think, like, for example, you find like a lot of assignment first. And then based on the assignment, you plan the trajectory, right?
Right. But let's not forget that in that particular case, we do not consider collision avoidance stuff in it. It's just coupled PATO versus PA plus TO.
Yeah, but what if you get assignment while that's actually not feasible? Will you do another re-planning for the assignment?
What do you mean?
Because, for example, on step 1, you disregard collision constraints, right? And what if you got this alignment and realize that there is possible to find such a path for this alignment, and you will need to find another alignment. What's the name of it?
So that was considered in the second approach, where we explicitly consider collision avoidance in the assignment.
What if there is no solution at all for the second part?
Then, so to guarantee feasibility in that case, we reduce the R-safe requirement. So the R-safe was the safety distance, right? So if we minimize it to 0, we see like there is a solution. For R-safe, for some value of R-safe star, there is no solution. So there has to be some point up to which there is some feasible solution between 0 and R-safe star.
I mean, the solution is just empty set.
So we see that for the nominal case there exists a solution. Otherwise, we can't do anything. For the nominal case, I mean like when there is no threat of collision. Is that problem solvable with that case?
Yeah, and especially because you don't have any additional obstacles, right?
No.
Yeah.
In that case, no.
Yeah, so I'll make it a feasible, but there are no more obstacles.
But in the second step, you have obstacle. That's why you have the second step. But
No. By obstacles, he meant like beyond the satellite, is there any other external obstacles? No. In that example, only obstacles are neighboring satellites.
Oh, okay. And how do you optimize the fuel and the first step when you have not yet
So
tried the pass on the second step? Is that a heuristic thing or?
So each agent computes the path to the final location information.
But that's
So-
on the second step.
In the first step as well, but with a reduced step size that you can run it really quickly. Like,
Okay. Thank you.
and I showed the computation time, like it's really small, even though you have hundreds of satellites, because each agent is computing for 100 different positions in a decentralized manner. Yeah, so, like,
I just feel like it's really similar to the task and the motion tracking problem in the classic planning theory. While you have tasks in like discretized manner, only here you have reconfiguration on the first step, and you do what that you have at the second step. It's similar.
Do we have any other question?
and anyone in the Zoom room, do they have? Oh, okay. There is no other participants.
Awesome. Okay, thank you, Himadri, for your
Yeah.
presentation.